Hey everybody, so we're continuing on, we're moving on from exponential regression into some other curved varieties that we will need to figure out how to straighten out. And we're going to be looking at power models. This is actually the next to last new thing we're going to learn. So we're winding it down, we're getting there. And so let's go ahead and start. So yeah, when we were doing exponential, that's your parent function, and the issue here was that we typically had time as our explanatory variable, and time is linear. I mean, it just produces at a constant additive rate. So when we did this and we had a curved relationship, we straightened it out by taking the log of the response variable, because the y's, or the predicted outputs, were the ones that were contributing the curve. But what happens if the x is also contributing to the curve nature? I mean, there are other kinds of curves beyond just exponential. We have quadratic, cubic, quartic, all different manner of things. And so that's where power models come in. So instead of y equals a times b to the x, y equals a times x to the b. For example, y equals x squared, y equals x to the third, y equals x to the eighth, that sort of thing. So we're talking about powers. So it's a power model. Quadratic, cubic, and really any other curved relationship can be modeled with a power model. This is where both your explanatory and response variables are contributing to the curved nature of the scatter plot. So as such, we're not going to limit just straightening things out by taking the log of the response variable. We're also going to be taking the log of the input or the explanatory variable. And hopefully that will straighten things out, and then we can get into a linear model and do linear procedures and interpretations and whatnot. Just keep in mind, especially if you read what your author has to say about this, that there are going to be relationships where doing, logging both your x and y values, this just won't straighten things out. And that's just one of those things. If you encounter something like that, just look at what you started with originally, and does it look cubic? Does it look logarithmic? What does it look like? If it looks like something identifiable to where there is a regression that exists for it, then that's what we're going to be stuck doing. But until then, we're going to try to straighten things out and make a linear model out of it. So power models, just FYI, are used in variables that are in different dimensions. So we could input gallons of paint in order to predict surface to paint. And remember, gallons is a three-dimensional value. It's based on volume. And surface area to paint is 2 dimensions. Length times width is area. All right, so to use a power model, take the log or natural log. Your College Board loves natural log. So that just changes things up. Instead of base 10, it's base e. But we're going to do it for both x and y and see if that doesn't get us to a linear relationship. So if you look at this, y equals a times x to the b. If you take the log of both sides, here's what happens. You can use rules for exponents. Remember, this will be log a plus log x to the b, and you can move the b to the front. Well, that becomes a constant, that becomes a constant, that's a slope, and that's a constant. So we're talking about constant equals y-intercept plus slope times a constant, or y equals a plus b times x, which is linear. So hopefully taking the log of both sides will push your curved relationships to linear. All right, so let's go ahead and look at the example. We can close this out. That's in your packet. And I believe this is the distance in astronomical units. Looking like we're on pages 16 and 17 in your packet. So if you turn to page 16, this is what we've got. We've got data gathered by astronomers of the distance from the sun of the planets in our solar system, this is in astronomical units, versus the period of revolution of those planets. I'm guessing the thinking here is if you can get a predictive model, then you can possibly predict how far away unknown planets are beyond the visible solar system. I don't know. I'm not an expert in space or physics or anything like that, but we do have bivariate data, and keep in mind your distance from the sun is not time. So there's every reason to think that that distance will not excuse me, have a linear relationship, nor will the period of revolution. So let's see how it goes. So in your calculator, I have this set up. Distance, astronomical units, period of revolution. And so what I need for you to do is go ahead and set up with these two variables, put in your data, and go ahead and pause while you do that. Okay, so now that you're back, let's go ahead and let's pretend perhaps this is, well, let's look at the relationship just as it stands. So let's go to the home screen, scoot over, we'll create a scatter plot, and we're using distance to predict revolution period, and wow, that looks almost exponential. So let's pretend it is. And let's go back to our data, and we'll scoot over here, and if it were exponential, we'd be taking the log or natural log of the output, which is period. So let's go ahead and give this a name, LPD, so that we can kind of keep connections. All right, so LPD, and this will equal, so we need a formula, and let's go ahead and control 10 to the x for log. We'll keep it base 10. And we'll just say PD because that's an established variable that we've set up, and hit enter. And let's see what that does to the scatter plot. So let's go over to here, and we just need to change the output from PD to LPD. And wow, that did not straighten things out. Looks really curved. I don't know. It looks almost logarithmic, but we have straightened out whatever the output is. That means that the curve is now pretty much all assigned to your input. So let's come back here and let's scoot over one more, and we're going to do LDIST for the log of it. Continue to wish this had a QWERTY keyboard. So this will equal control log base 10, and this is going to be DIST. So hit enter. All right, let's see if that straightens out if we put both logs into our scatter plot. So instead of doing distance here, we'll change it to log of the distance. And yeah, wow, that really straightened it out. So we definitely have a power model at work here. And now that it's looking pretty linear, we can go ahead and just do linear calculations on it. So, well, let's review and see how we've done with the notes part of it. All right. So we did the scatter plot originally, and it was curved, looked like it was exponential. So we treated it like exponential and did log of the output, and it looked almost logarithmic. So then we took the log of the output to straighten out, the input rather, the log of the distance, and that did seem to straighten it out. So then the nature of the scatter plot we ended up with became positive, linear, and strong. So now that it's linear, let's come back here and create the linear model, all right? So we'll go home and we'll scoot over to here and hit enter. And let's go ahead and do menu, statistics, stat calc. Since we made it linear, let's go with linear regression a plus bx. All right, the input will be the log of the distance, and the output will be log of the period. And we'll keep this at F1 and 1, so tab down to OK. All right, look at r and r squared. Nearly perfect. All right, so here's A and here's B. So we can start recording. Okay, so this is what we ended up with. Remember, you took the log of the input, you have the log of the predicted outputs, so you need that in your formula. So when you go ahead and do this, you'll input for x, take the log of it, so it's like log in, and then when you're done, you have to anti-log to get the original metric back. So x is the distance from the sun, y hat is the predicted period of revolution, here's r and r squared. All right, so in interpreting the slope, you're going to do it exactly the same way that you would do it had you not taken the log, but since you did, you're just going to add in the log designations. So for each increase of, I guess, 1 unit of the log distance from the sun, there is a 0.000083 decrease, right, negative, in the log of the period of revolution about the sun. And interpret r squared, well, almost. It can never actually be 100%, even though it gave it to us as 1. It just was so close to 1 that it just, boop, defaulted to it. So almost 100% of the variation in the log of the period of revolution about the sun can be explained by the variation in the log of distance from the sun. Same thing, we just threw in the log designations and made it good to go. All right, so because of anomaly in the motion of the known planets, astronomers feel that there is an indication of a new planet in the solar system. And so they calculate the average distance of the new planet from the sun to be 102.15 astronomical units. Now that is extrapolation. I don't like that. It's not a good thing. It's never a good thing. So I noted that it was. But keep in mind, these are physical systems rather than just social systems or biological systems. So, you know, they tend to stay intact beyond the usable domain. But I don't know, it is pretty hazardous. So just note that you did it. So here's your model. Input 102.15. Take the log of it, multiply by 1.5, add on this y-intercept, and you get this. 3.01377, and you need to, that's going to go on base 10 in order to give you your original metric. So just use both of these as exponents to put on base 10, and you notice when the two bases here are the same, the y-hat drops out, this becomes a number, and it is, the input was way beyond 39.529, so you would expect the output to be way beyond this output of 248.530, so you get 1032.23 years as a prediction, be it an extrapolation or whatever. All right, so in your calculator, we should be able to do that. All right, so if we go ahead and do the let's see, the log of that number. So let's just go ahead and do control log base 10, and it was 102.15, right? All right, so let's go ahead and store that. So we can just do control store x, enter. And then we can run that value through the this stored equation. Remember, it's stored as F1. So let's see, F1 and parentheses, and we stored that as X. So let's go ahead and do that. And remember that number, 3.01377? Remember that one? It was right here. So now all we need to do is store that number. And I'll just store it as x again, which will overwrite what I had, and then just do 10 to the x. And there it is. There is your prediction. So it's log in, anti-log out. If that calculator process confused you, just write out your LSRL, input your value, take it down to a number, raise both sides of your equation, or rather use both sides of your equation for exponents on base 10, and your answer drops right out. Okay? So that's power models. We can actually look at residuals just like we did for exponential. I don't think you really need it for homework or anything, but if we go back to your scatter plot, we can change this to stat resid. And again, you can see these two and these three are where growth is occurring faster than the model predicts, or your predictions go beyond what your model predicts. This one is pretty much dead on, and these three come up short of what the model predicts. So, but that's how you interpret it. All right, so let's go ahead and mark a close to this. This completes your notes, and go ahead and do the assignment. I believe it's number 122, and that will pretty much complete the week that we missed due to Corona. I'm not exactly sure. I'm just doing this on a Wednesday during our first week off, so I still haven't heard anything from the district. I don't know how the calendar is going to fall out. What I'd like to do is just take that missing week and move it a week forward, but I just don't know what I'm going to be required to do. So let's just play it by ear, and I will put up notices that will clarify and modify anything that needs to be changed. So on that note, stay safe, and until next time.